Thank you for your kind introductions. So I'm Akihisa Goban, CTO at NanoQT, where we built quantum interconnect hardware using all fiber-based cavity, which is compatible with neutral atom technologies. So let me briefly overview our companies. We started about 3 years ago based on this low-loss, all fiber-based cavity, which can enable efficient interaction between neutral atoms and photons. Also, seamlessly integrate into optical fiber network, because by design, this is made of fibers. And we expanded our team up to 10 PhD and additional engineers. And now we are supported by venture capitals and also the government funding, both from US and Japan. Although our technology is deeply rooted in Japan, we transfer our headquarters to California, and we have operation in Maryland, and also all the hardware R&D is still in Tokyo. So let's switch gears. As we already have heard about scaling of QPU has needed a lot of new technologies, and particularly one promising direction is using the modular designs. The quantum interconnect will enable the orchestrated computation using multiple QPU by distributing entanglement as a resource. In the short term, this will be like within the data center, short distance network, but this quantum interconnect can work as a repeater as well, so you can send the entanglement to a longer distance. That will contribute to the large-scale quantum networks. So what is the requirement for this quantum network interconnect devices? Particularly when we want to use it for the quantum computation with error corrections. There's a few specifics. Once, quantum interconnect device has to synchronize with your quantum error correction cycles. So we are thinking about neutral atoms. That's typically like a milliseconds. And then, in order to use it for the error correcting cycle, you need to have an error correctable entanglement, so-called logical entanglement. To make logical entanglement from the physical, that's noisy entanglement, you typically need the factor of 10 moles, even if you start with a 1%. You still have an efficient distillation code, but you have an overhead here. And in order to do the efficient circuit comparisons, you still want to have about factor at least order 10 logical behavior per error cycles. So that means you need about 100 physical entanglement per error cycle, per milliseconds, which gives you the required rate of 100 kilohertz, and also the error rate of 1%. And again, once you generate this logical behavior, you have to bring this qubit to the computation so that seamless integration between the interconnected device to the QPU is a critical component. Those are the implications to the hardwares. So we need efficient photon correction through the cavities, as we had in the previous talk, and integration to the QPU is critical. So our approach is using all fiber-based cavities. So we take standard fibers, and we specially manufacture such that the central region is sub-microns. So photons still propagate inside, but part of the energy leak out as an evanescent field. So even if you place atom outside, these atoms can interact with the photons strongly. So in our fabrication technology, we can suppress the loss such that we reach the propagation loss below 1 dB per meters. So single pass corresponds to 0.1%. And this nanofiber region is about 1 millimeters, which is quite long as a nanophotonic standard. So even if you place atom every 5 microns, this can fit 200 atoms. And eventually, we need to make a cavity. So we fabricate the in-fiber mirror called fiber black grating in-house to circulate the photon in between these two. In this way, we can achieve the finesse 4000, meaning that you can circulate photon 1,000 times. That's your enhancement factors. And most importantly, as I mentioned before, this system is seamlessly integrated with the neutral atom optical tweezer technologies. So you transfer the atom from free space to near the nanofibers, and then you put atom there, but still you have enough interaction between them. So our architecture design is following. So you have an interconnect device, nanofiber cavity, which generates the remote entanglement between neighboring nodes. And once you establish this entanglement by photon click, so you can tell which atoms are entangled. and you transport those atoms to the QPUs. In this way, if you have 200 atoms, you are projected to reach 100 kilohertz rate. That's marginally sufficient for useful applications. But of course, if we want to run more complicated circuit, you need to have a higher rate. So we are currently working on integrated fiber arrays to further increase the rate by channel multiplexing. And in terms of the atom size, we intentionally choose ytterbium atoms, which naturally has a telecom band transitions, so you can directly interface with the long-distance communications. So this system will work not only as an interconnect device for the computations, but also for the repeater applications. Here's one of the prototype machines. We trap 5 atoms near the nanofibers, and by transporting those atoms near the nanofiber and interface to the cavities, we generate a single photon at rate of kilohertz. So this is with only single atoms, so by increasing the number of atoms, we expected to boost the rate up to 5 kilohertz with the 5 atoms. So here's a near-term milestones. In 2 years, we aim to generate entanglement around 10 kilohertz, which means eventually you can get 1 logical bell pair per 1 quantum error correcting cycle. So you begin to do something interesting in the remote fashions. So this will be done with the 20 atoms. And eventually, we want to go up to 200 atoms, where you can saturate the performance of the cavities. So even if you increase the number beyond 200, the rate doesn't increase because cavity has a finite bandwidth. That's where we need to increase the number of nanofiber cavity with a channel multiplexing. So to achieve these milestones, there are a lot of technical challenges and fundamental challenges. So we address these key challenges in the highlighted recent papers. So in our perspective paper, we describe our architecture design, how we can speed up the entanglement generation. And in the following paper, we also address one of the error rate, which is intrinsic to the photon generations. So every time you emit a photon, you get a kick from the photon emissions. So we find a remedy to minimize those effects. And most recently, about 2 days ago, we posted this architecture paper, which describes how we come up with a scalable design with the neutral atoms that is compatible with the interconnect devices. And we have several application papers coming up, and we are actively looking for the partner and collaboration to further accelerate our R&D and the theory architecture design. So if you have interest, please feel free to ask me. Thank you for your attention.